Good morning, sir. I am Rohini from Electronics and Communication Engineering Department, third year. And here I'm going to present my assignment video on topic demonstrate direct form 1, direct form 2, cascade and parallel realizations for Chebyshev filters with frequency transformations for band pass conversions. Here my subject name is Digital Signal Processing and subject code is 23EC601. Understanding Chebyshev filters and their relations. Digital filters are the fundamental components in modern signal processing systems, enables engineers to selectively pass or reject specific frequency components from signals. Unlike Butterworth filters, which provides a maximally flat response, Chebyshev filters allow for control ripple in either the passband or stop band, resulting in steeper roll-off rates. These characteristics make them ideal for applications requiring rapid transition between passband and stop band such as audio processing, telecommunications, and biomedical signal analysis. Introduction to filter realizations. What are filter realizations? Filter realizations refers to the specific implementation structure used to convert a mathematical transfer function into a practical digital filter. So the choice of realizations affects several critical performance metrics including computational complexity, memory requirements, and numerical stability. So why multiple realizations exist? Different realization structures emerged from the need to optimize various aspects of filter implementations. For instance, direct form 2 reduces memory requirements, cascade relations improves numerical stability for higher order filters, and parallel relations offers advantages in certain filter types. So the choice depends on the system constraints, available computational resources, and hardware. Direct form 1 relations. Direct form 1 represents the most straightforward implementation of a digital filters transfer function. It directly implements the difference equation by computing the output as a weighted sum of past inputs and past outputs. This structure follows naturally from the mathematical definition of the filter, making it intuitive and easy to understand. The mathematical foundation is the general transfer function of a infinite impulse response filter is h of z is equals to summation k is equals to 0 to m bk z power minus k divided by 1 plus summation k is equals to 1 to n ak z power minus k. So the corresponding difference equation becomes y of n is equals to summation k is equals to 0 to m bx x of n minus k minus summation k is equals to 1 to n ak y of n minus k. In direct form 1, we implement this equation directly requiring separate delay chains for both inputs and outputs. These are the steps we follow. First step is input delay chain, second step is feed forward path, third is output delay chains, fourth is feedback path, and fifth is final output. Direct form 1 is particularly used for education purposes and low order filters. However, its requirements for separate delay chains make it less efficient for higher order filters. Direct form 2 relations. A direct form 2, it is also known as canonical form, represents a more efficient implementation of the same transfer function by recognizing that the input and output delay chains in direct form 1 contains redundant information. This structure combines them into a single delay chain, significantly reducing memory requirements. Implementation details are the structure interchanges the order of feed forward and feedback sections, allowing them to share a same delay elements. The intermediate signal W of n represents the state variable. W of n is equals to x of n minus summation k is equals to 1 to n ak W of n minus k. So output is y of n is equals to summation k is equals to 0 to m bk W of n minus k. These are the steps we have to follow. First is input signal, second is state calculation, third one is state delays, fourth one is output generation. But direct form 2 offers memory efficiency. It has more practical considerations. The structure can be sensitive to coefficient quantization errors, particularly for filters with the poles close to the unit circle. Cascade relations. Cascade relations, it is also known as series relations. It decomposes a higher order filter into a sequence of second order sections connecting in series. These approaches are orders numerical stability issues that arises when implementing higher order filters directly, making it one of the most popular relations methods in practical applications. So why we are going for cascade? Higher order filters implemented directly can suffer from numerical instability due to coefficients and sensitivity and round of errors. So by breaking the filter into second order sections, we reduce these effects significantly. Transfer function factorization is the overall transfer function h of z is factorized into a product of second order sections. H of z is equals to I is equals to 1 to m h is of z. Second order sections. Each backward section implements a second order transfer function, typically with complex conjugate poles for real filters. Implementation structure. The cascade structure connects multiple backward sections sequentially. The output of one section between the input to the next. Each section can be implemented using direct form 1 or direct form 2. The choice of section ordering in cascade relation significantly impacts filter performance. Engineers typically order sections based on the pole radius, placing sections with poles closest to the unit circle, last to minimize noise applications. Parallel relations. Parallel relation represents an alternative decomposition strategy where the filter transfer function is expressed as a sum of simpler transfer functions rather than a product. This approach proves particularly advantageous for certain filter types and offers unique benefits in specific applications. The mathematical decomposition is the overall transfer function is expressed as a sum of partial fractions. So h of z is equals to summation I is equals to 1 to m hi of z. Each component filter hi of z can be implemented independently and their outputs are summed to produce a final result. Implementation architecture is multiple filter sections process the same input signal simultaneously. Each section operates on the full input and their outputs combine through summations. This contrasts with the cascade relations where each section processes the output of the previous section. When to use parallel relations? Finite impulse response filters with symmetric impulse response, filters requiring minimal phase distortion, applications needing fault tolerance, signals with parallel processing capability, and more. Comparison with cascade. While cascade relations excels at numerical stability for higher order infinite impulse response filters, parallel relations shines when dealing with filters that have poles far away from the unit circle. So the parallel structure also allows for graceful degradation. If one section fails, the filter continues operating with reduced performance rather than complete failure. Frequency transformation basics, shifting and scaling filter responses. Frequency transformation techniques enable engineers to convert a prototype low pass filter into a filter types without redesigning from scratch. This powerful approach leverages the well established design methods for low pass filters and extend them to create filters with more complex frequency responses. Low pass to low pass, low pass to high pass, low pass to band pass, low pass to band stop. And mathematical foundation is z power minus 1 can be written as z power minus 1 plus a by 1 plus a into z power minus 1. The band pass conversion using frequency transformation steps are: first we need to prototype low pass design and determine the band pass specifications and calculate transformation parameters. And fourth step is apply frequency mapping, and fifth step is verify and implement. Key takeaways and practical applications in filter design. Understanding different filter relation structures and frequency transformation techniques empowers engineers to design efficient and stable digital filters for diverse applications. And here, relation selection, frequency transformation, numerical stability, and resources optimizations are the key takeaways. Practical applications across industries. Here we can use these relations in telecommunications, audio processing, biomedical engineering. First, we need to understand prototype design and consider implementation platform, and we can verify stability and response. Thank you, sir.